We're on activity 8, and we're going to talk about modular art and Bezier uh, curves. So we want to start out talking about modular art, just in general. And it's what's a modern description of modular art? And so I want to get that in here. All right. Now, this is a pretty good description of what really I wanted to talk about, in the beginning here. You see these pieces, they're all squares, and they're kind of just filled in this space. This is an irregular shape, and a lot of times you'll see modular art used on irregular spaces because, again, they do have the flexibility to move pieces around and all that. And the pieces share some different things. So you'll see some lines. They all have this one vertical, one horizontal line along the sides on all of them. And there's some circles on all of them and different colors or consistency through those. And we see another one here. All these shapes are basically the wood part are basically the same. And then they also inside have these blue geometric shapes in them. And then they're kind of randomly positioned around, trying to fill up this irregular wall here. And again, this is a little more consistent. It's easy to see. We have these squares with these perpendicular lines, one across the horizontal, one vertical, and they all have the red circle on them. So they're consistent, but not exactly the same. And there are some things that may be exactly the same on them. But again, the idea is not that they're all exactly the same. So it says that this ART, Art Rethought, launched its first fully customizable modular art collection with scalable contemporary geometric art modules that can be pieced together in an infinite number of ways. It's designed by artist and architect Don Ratner and so on. So that's the idea. Is again, they can be size-wise when they say scalable, and again, the geometric art. And so let's go ahead and go to number 2 here. It says, explain 2 specific approaches to creating modular art. And again, this first one, if I can get to it. All right, I got. And this is an idea of creating modular game art for fast level design. And so when we think about, again, modular pieces, we said that there's some things that stay the same and that are exactly the same about the pieces, remain consistent. And he goes through and explains about setting up the different formats for like walls or so on, and different pieces that could be used within there. He says models with random shape, floating in air, have a good pivot points. So again, here's some different pieces that they use at different levels and so on. And so so this idea of modular art is pretty appropriate for game art also. And then and this is something a little bit different. It's kind of again modular art, but this modular art system. It says a 1-year art project, and what it is you can build your own website where you can create dynamic artworks by interacting with different elements and you'll see how they quickly kind of create a design. You put these pieces together, build your own configurable wall art. And then there's a video you can watch. I'm not going to go through, but you can see that's pretty unique, pretty nice colors though. A lot of lines and colors, and you could probably think about maybe something even that you would customize that to something you had liked or wanted to remain the same in some type of artworks. And so again, another neat idea, neat use of modular art. And of course, we want to talk about the ways you can, use mathematics to help you create modular art. And we're just going to do one type. There's lots and lots and lots, an infinite number of types of modular art you can create. And the one thing we want to talk about here first is rotational symmetry. So we're going to borrow this idea from mathematics or geometry. And so we talked about point symmetry and line symmetry and origin symmetry before, and now they're talking about rotational. And it's a fairly simple idea. It just says rotational symmetry or radial symmetry in biology is a property a shape has when it looks the same after some rotation by partial turn. And so if you go down here and look at these, like they call this C2 rotational symmetry, but they had here somewhere. Okay, we'll just get, but the um, the idea is that you can turn this thing one time. You're kind of halfway through or 180 degrees, and it looks the same. Then you turn it one more time. So two times gets it back to the original. So 360-degree turn, you go really two turns. So this has C2, what they call C2. And then C3 would be, again, this would take three turns to get it back to the original three 120-degree turns. Now, each time you turn it 120 degrees, it looks exactly the same from the way it started. And again, so you have 4 and 5 and 6 and the whole ways up. And then they go through, if you want to look into the math, you can see it gets fairly complicated. Um, but for our purposes, we just want to look at really basic idea of rotational symmetry, and that's all it is. It's pretty simple. All right, so again, we can have like twofold, threefold, fourfold rotational symmetry. And we're going to talk about fourfold actually, and modular arithmetic. So we're just going to talk about one type, fourfold rotational symmetry and modular arithmetic. Okay, and in fact, it's just going to be addition, modular addition. So what is modular arithmetic? And again, I'm going to kind of go quickly through this, but it's a very basic idea of working with integers that only have certain amount of numbers that you can work with. And a lot of times people talk about clocks. Now, this was introduced by Carl Gauss in around 1801. And the idea was to apply to a few different systems that he was working on. And so you notice that there was a lot of time in math went by before anybody even introduced this idea. That's pretty late in development for arithmetic. But it has to deal with kind of like a clock idea, because when you use a clock, if you start at 0 or 12, and then you start to go around to 3 to 6 to 9, and then you run out of numbers, it doesn't keep going up. Then you use the same 12 numbers over and over and over and over again. And So that's called a modular system. And we have lots of different types of modular systems out there. And what we have to realize is that there is something similar about the modular clock, but also something different about the numbers on the modular clock. Because if I say I start at 0 and I go to 3, and let's say that it is time, so 3 hours went by, and then uh, I go around in 3 hours, and it's 9, and then 12. But then after that, if I go another 3 hours, I'm back to 3 again. So those two time periods are what we refer to as congruent because they're both 3 o'clock, but we know they're not the exact same time in history or in measurement of time. It's a different time, right? It's at a different time period um, in maybe our lives or in a lunar rotation or or a pass around the sun or something like that. When we measure how long it takes for something to occur, because we really know that this is from here to here is 3, but if we go from here to here, 12 hours goes by and 3 more, that really meant 15 hours went by. But it's still represented as a 3. So 15 is congruent to a 3 in a modular clock, all right? So there's two things that happen in modular systems is that we don't really care that it's 15. All we need to know is that it's 3 past 0. That's all. So 15, and then if you go around 12 more times, and then it's 28, and so on, 41. So we just want to know maybe what position are we on at any given time? Are we on this 3? Something specific, like on a assembly line, may be happening at time 3, regardless of what day it is, morning, evening, day of the month, week, year. Maybe we don't care because we just know that when we're at point 3, a certain exact same thing is happening. So there's lots of uses of modular systems in manufacturing and in computers and in biology and in space travel and so on. So, all right, so let's go back. And so we have this arithmetic, this kind of rotational wrapping around of numbers. And again, we talked about who was introduced by it. It says here, two integers A and B are said to be congruent if, and there's a video here you can watch, and he goes through and explains like 3 different ways how you can view that. But what I want to show you is, again, just with the mod clock, because that's all we're going to talk about today. And so we want to know, well, what is this integers A and B are said to be congruent mod n if? Well, you can have any mod system, or you can have any clock with as many numbers on it that you want. So for example, let's go over to here. Here's a mod clock. It's a mod 5 clock. It goes 0, 1, 2, 3, and 4. There's no 5 there, but there are 5 different numbers here that we're using. Position 0, position 1, position 2, position 3, position 4. So that's why we call it a mod 5 arithmetic clock. We have 5 different positions on this. Okay. So what do we mean by things are congruent? Well, let me just put this down here for a minute. And let's look at this. 27 is congruent to what in mod 4? What does that mean? All right. So 27. Oops. And let me try that again. And for some reason, oops, there it is. 27 now is congruent to, is like an equal sign with 3 bars. 27 is congruent to a what in mod 4. Okay, so let's try that one. And what we're really trying to say is what position are we at on the clock, on a mod 4 clock, where we have numbers 0, 1, 2, and 3. Now, where are we if I started at the beginning and counted to 27, just kept going around and around? Where am I at? Well, basically, the easiest way to do that is to just take the mod. So you're going to take 27 divided by 4. So you take this number, whatever it is here, and you divide by this mod. You do the longhand. You say 6 times 4, right? 24. Remainder 3. So that's my congruence right there, the 3. So let's see if that's true. And this is going to be, I'm going to just draw a quick circle, very rough circle. 0, 1, 2, 3. So what we're saying is if I started here and I counted 1, 2, 3, 4, keep counting 5, 6, 7, 8, 9, 10, 11, 12, 16, 20, 21, 22, 23, 24, 25, 26, 27, right? So when I counted to 27, I ended up on a 3. That's what the remainder told us. The remainder of dividing these two numbers, okay, this divided by this, tells us where we're at on the clock. So it's just kind of a quick, so that's one use of using modular numbers in a modular system, is to find position regardless of what the number is. So that's a pretty easy way to come up with that. And let me clear that canvas out and go back. And I'm just going to do one more. 133 is congruent to what in mod 8? Right, 133 is congruent to what in mod 8? So 133 is congruent to what in mod 8? Okay. And so again, I'm going to take 133 divided by 8. So 1 times 8 is 8. 8, 5, and 3, right? So I subtract, I bring that next one down. 6 times 8, 6 times 8 is 48. Subtract this, I got a bar, right? Remember that? 8, 5. I got 5. That's my answer right here, right? There's my answer, 5. So again, if I had a clock, I've had a clock 0, 1, 2, 3, 4, 5, 6, 7. If I had a mod 8 clock and I would count 0, 1, 2, and 8, and 16, and 24, and I kept counting the whole ways up to 133, 131, 132, 133, I would be right there. I'd end up on 5. So that's what we mean. It's 133 is congruent to 5 in a mod 8 system. All right, so we're going to move on. So a little bit of basic math, integer math. All right, so let's look at how we're going to use that, because we're going to complete a mod table and then it's going to help us create a design with rotational symmetry and mod 5 addition into it. So again, list 5 applications of modular arithmetic. You can look at the we talked about astronomy and biology and art, for sure, art, but computers and so on. So the art applications the one we're focusing on, and we want to complete this mod 5 table right here. All right, so we're going to need, and this is a very simple idea. This is just like back in probably second grade. You did these tables, addition and multiplication tables. So you took 0 times 0, 0, or 0 plus 0, 0, 0 plus 1 is 1, 2, 3, 4. So you'd fill this all out. But now there's a little bit of an issue here because when we get to the higher numbers here, like 3 plus 3, we would put 6 right here in a regular base 10 table. But we don't have a 6 in mod 5. So what we're doing is we're finding the position, right? That's, remember we said we just went on that mod clock trying to find what position are we at. Quick way to find them in bigger numbers, right? So now I kind of worked this out. Well, I found a thing here, and we're just going to use this. But basically, to fill that table out here, right? To fill this out, we would go through like this. And let's say, so I said, 3 plus 3 is 6. Well, let's see. If we start here at 0 and we go 1, 2, 3, 4, 5, 6. So 6 is congruent to 1 in a mod 5 system. So that's why there's a 1 right here. Took 3 plus 3 and you got a 1. And let's say 4 plus 4 is 8. Well, let's see. 0. So we go 1, 2, 3, 4, 5, 6. At least 1, 2, 3, 4, 5, 6, 7, 8. There we go. So an 8 is congruent to 3 in a mod 5 system. That's why there's a 3 right here. 4 plus 4 is 8, but 8's congruent to a 3. So see, all these numbers go, and they fit. They're one of these numbers here. So we need this. All right, so we got the table, and now we want to do assignment 1. Now this assignment's going to take a little bit of time, so you may want to go to the Canvas website, go to the mod 5 table that's listed there, and I'll pull that up, and then we'll come back to this in a little bit. So let's put this here, and we're going to put this here. Okay. Okay. All right. Let me make this a little bit smaller so we can see the whole thing. There we go. And again, we don't need this one. We don't need the clock anymore. We just need this right here. All right, so now we got to fill this up with something. And this is guiding us. Now, the first thing you got to do is your design is really, there's an infinite number of possibilities. We have these numbers 0, 1, 2, 3, and 4. 0, 1, 2, 3, and 4. So we have a little square for each of the numbers. And those are going to be our definitions. You can put anything in these. You can make them all different, which is normally what happens. Or you can have some the same or nothing or whatever. So it's just lots and lots of flexibility on this. And also you can change this operation to any mathematical function or operation that there is. So you can get some really neat stuff. You can make the mod tables as big as you want. You can get as much detail as you want. And so they're really, really just endless opportunities. This is like the most basic one, mostly because of time here. Now, so what we have to do is we're going to define these, and each of you really can put whatever you want in there. I'm going to go in here and draw, and it's going to be kind of rough drawing, my writing, plus being on a tablet. It's not that great, but it'll work. All right, so I'm going to come in here, and for 0, I'm just going to draw a line. I want to make this simple because this is going to take us some time. So I'm going to make it as simple as possible. Okay. Oops. Let's see. What do we got here? Yeah. So this is going to be a straight line right like that. That's it. Okay. That's my 0. And basically, everywhere there's a 0 here is going to have that in these right here. All right. So a 1 is going to, I'm just going to come down here and kind of fill this in very quickly. So roughly, I'll fix those up later. A 2 is going to be just that. Again, I'm making this up. You just put in anything, absolutely anything. I'll only leave the 3 blank. Give me some white space. And a 4, I'm going to put a little arc up here with fill that in. I'll fill those in better later. Okay, so all right, those are my definitions. Now we're going to do this thing 4 times. So if we come over here for a minute, this row ignore, this column ignore. We're not using that at all. Okay, we're using these numbers in here, just these ones in here that match 1, 2, 3, 4, 5. These in here. Okay, so in other words, this 0 is talking about this space right here, right? This cell in this little matrix table. So I put a 0. Well, there's my 0. It's just a line right here. Okay. Well, there's zeros over here also. So that means I got to put them. I got to come down. I got to put 0 here, here, here. All right. So there's my. All right. There's my zeros. And again, because that's where it's supposed to go, right there. This thing's telling me where to put everything. Now, we have to do this exact same thing 4 times. It's better to do it right now instead of wait till later. So let's very quickly, I'm going to put these in this one, this in this one. So like a photocopy image of this thing 4 times. Put these in here, 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 here. All right. And again, that's why I'm trying to keep it simple because I want to be able to do this quickly. All right, so we're done with the zeros. That's it. No more zeros, nothing with that. Now here's a number 1. Okay, where does the 1s go? They go right here and here and over here. So this is the second one over along the first row. So that's right here. And 1 down here. So this one goes right here. Right. And then I got 3 of them over here. I got to put right here. And again, you can take your time when you do yours and make it a little bit cleaner. It'll look nicer at the end. I just kind of throwing this together. So I'm going to do all these. Can't forget these ones. And so you get the idea. It's just going to repeat this. And if I eventually do forget something, I mean, once you see, you'll at the end, you'll be able to tell it's missing. Fill it in at the end. But I just would like to make this look fairly reasonable for you, so you know we got to fill these all in. All right. So that looks good. The twos, all right, the twos, oh, they're just going right down along the side there and for these two. So a two is just this, up and down, up to the middle. So I got up, down. One, two, three. And then I need the twos down here. Probably help to have a straight edge, right? But that would take too long. I could do that with the straight edge here. But again, okay, the three I left blank because again, I'm trying to save time basically, or I got some white space. So these are threes and this one. All right, let's go to the fours. The four is just this little thing up in the corner, and that's the diagonal right down the middle, right here. So I'm gonna do that down the diagonals, right down the middle here. Just gonna put this little thing here up in the corner. Always around very quickly. Make them a little smaller. And we're almost done with this, right? So now you need a pair of scissors. So you got your paper. You're gonna have to print it out or digitally put it together. But basically, what you have to do now is I printed it out, took a pair of scissors, and what you do is you cut these pieces out. So you have four things that look exactly the same. Right? So again, you cut this along here, up, over, up, up. Then you got to cut this one out. Okay, and then you got to cut this. So you got four of the exact same thing here, right? All cut out. Then the rotational symmetry comes in. As these stand, what you do is you take this one and rotate it clockwise 90 degrees. So you rotate it 90 degrees. This one you rotate 180 degrees, so that's two turns. This goes 270 degrees, so you turn this thing three times basically. And then you put it together and tape it together. And I'll show you, I taped mine. I cut it out. I just did this and I scanned it. If I can find it there, let me see, image 12. And I cleaned it up a little bit so I filled these spaces in, but you can see the difference, the symmetry, just from this little simple activity, um, like this. I mean, this looks really like nothing. It's pretty bad kind of thing. And again, not that this is clean, but just by taking these four pieces and adding rotational symmetry in, in 5 minutes, like this looks pretty good. I got a nice design going here. I could really clean that up and do some shading or bordering around this and have a very nice pattern. I could do something in here unique with it. You got lots of options that you can do with this. So again, 5 minutes came up with something that looks pretty decent. And again, just from taking from this to this, all we did was rotated these 90, 180, 270, and got to rotational symmetry. So symmetry can very much add a lot to an image. Okay, so that's it. So you'll basically that's a big part of the assignment today. I tried to make this last one. So if you get this done, let's see if we can get through the rest of this. So I'm going to put that down and this and see if we can get back to the activity. There we go. So it's class one assignment one. Now, vector art, again, it's basically, using mathematical formulas to create designs. And they talk about, geometry and the importance of geometric shapes and using those. And on this link, they talk a little bit about how, like in animation, you have these wire frames that you use. They're scalable vector graphics, and because they're defined by geometries, um, and they say these basic mathematical shapes called primitives, and then they go through it and talk about, okay, here's some from a geometry standpoint. We have triangles and four-sided and 5 and 6 and 8 and so on, shapes that we could use. And again, it says we could use irregular polygons. Harder to create the mathematical formulas for these, but you could, and you can get that different ways. And he says, okay, well, let's start with a circle. And we did this last week. We had a circle, then we had an equation that looked like the circle. We did the ellipse, and then we did the super ellipse, and we did the super ellipse in 3D, and then we went to a super formula. Okay. And we know that those are very important. But here's a little bit of a different approach, very similar kind of thinking, but in a little bit different direction. These Bezier curves are kind of like the same. They were generated with the thoughts that these people had, Piet Hein and so on, with the super ellipse and a super formula. And so these Bezier curves, they talk about you can have a linear Bezier curves. And in algebra, you probably wrote the equation of a line. Here's a line, y equal mx plus b. That's slope-intercept form of a straight line. Okay, so how do you get that? Well, you take these 2 points and you can use this formula. This is the 2-point formula. Here's a slope formula. But basically, to get the slope, you use the 2 points, then you put them in there, then you use one of the points. And you can get the linear equation. So if you want, and they call that a linear Bezier curve. It's really just a linear equation. And so the quadratic equations, right, or quadratic, they call Bezier curves. Same idea. And it got the 3 points. And then you can solve a system of 3 equations and 3 unknowns. You have this y equal ax plus bx plus c. And then you plug in like the 1 for x and 2 for y. So here's the 1 for x, put in here for x, and the 2 for y, and you get this. And then you put the 3 and the 5 in another equation. So you put the 3 here, you square it, you get 9. You put 3 in here and you get 3b, and you put 5 in for y. And then you put the other point in. Then you solve these system of equations, and you get this. So again, this is going back to some algebra, college algebra, stuff like that. All right, so curves, those are good. They're good, but they're not enough. Okay, we can't really get some really good curves yet. We need to go one more. We need to talk about cubic Bezier curves. Well, to find cubic Bezier curves, or a third degree polynomial, which is what we have right here, we need 4 points. So you see you got 1, 2, 3, 4, right? And then you can get some nice curves out of that. All right. And there's a little activity here you can take a look at. We're just going to go ahead and move on and change that. All right. So, all right. So vector. All right. Now, so what type of functions are Bezier curves? And we've talked about, the XY coordinate axis, Cartesian coordinate plane. We talked about polar equations. And then last week we talked about parametric curves. And we said they're really important. And we find out that the Bezier curves are also parametric equations. Says the Bezier curve is a parametric curve used in computer graphics and related fields. And they relate back to these Bernstein polynomials. But this Pierre Bezier used these curves, these parametric curves, for designing bodies on Renaults. Okay, so he kind of may not have been exactly the first person to use them. We've had some other people mess around with them, but he probably developed them and really did most of the effort on getting these things going. So he wrote the cubic polynomials with parametric equations and then did his design work that way. And people liked it. They said, man, it's really neat. You can get all these neat curves. The computer seems to be able to handle it well. We can program this stuff in. And this, of course, was after he did, his stuff by hand, and that was in the 60s. But not much later, when people started looking what he was doing in the late 70s and then definitely the 80s, we started to use these a lot. And so let's go back. All right, so classroom assignment 2 is very straightforward. It says draw a simple curve using the control handles and Desmos. List for order pairs for your control points. Write out the set of parametric equations for one of the straight green lines. So let's take a look at this. So you just have to copy paste this and go into Desmos, and it's already done for you. Okay, so you don't have to do any work on this other than kind of play around and see, well, what do we mean by these 4 points defining the curve? Because the 4 points before, they were on the line, they were like on the curve and stuff, but this kind of not, but it kind of isn't when you define it parametrically. You're using linear interpolation, so that's what these lines are here for. So you're interpolating the points on here using these points. So if you move these around, you can see down here, let's go down, these points are changing, x sub 0, y sub 0. When I move that, oops, let me see, I got the wrong one. And it's got to be this one. There it is. So there's my x sub 0, y sub 0. You can see those moving, okay? So we have to take those points and plug them in and use parametric equations to define where that point is going to be placed. So we move these to where we want them. We put the curve to where we want them, and we say we have a curve right here, right? Let's put it here. Okay. So here's my points. This one is x sub 1, y sub 1, x sub 2, y sub 2, and x sub 3, y sub 3. Okay, so we got our 4 points. So let's look at the equation. Here is x sub 0, y sub 0. So to define this equation here, again, this is linear. So I'm going to use this one. Let me double check, make sure. There we go. There it is. Okay. So x sub 0, y sub 0. Right? Let's go up here. Well, what are the equations, the parametric equations? being used for that linear function right there. Part of my linear interpolation. Well, you put your x sub 0 here and your y sub 0 here. And they're in terms of t. Remember, parametric equations let x and y vary independent of each other. The independent variable is t. So t is what changes, right? T. And we have, here's the other point. And we're going to go down. Here's my x and y sub zeros, and here's my x and y sub 1. All right, so this line right here, is using these first 4 points. Here's my first ordered pair, here's my second ordered pair. So if I write the equation of that line for this particular curve, I've got x sub 0, y sub 0, x sub 1, y sub 1. Oh, I'm sorry, right there. I'm sorry, it's right here. X sub 1, y sub 1. There it is. And that would be my equation of that line. This one would be the next one here, these two. And this would be the third one here, okay, for these two. So you just have to pick that one out. You can pick this one out and plug the numbers in that you end up with for there. Write the equation. So that's all you're doing for classroom assignment 2. Move the curve, move the control handles around. Those are control points. They're vector control points. And control handles, right? We have the control handles. And you can move it around to position, and then that's it. All right, so let's see. What's an application for something like that, where you might have a simple handle you got to play around with? So Control C. Let's take a look at that. All right, let's get on there. But I do want to play this because it's very short, and okay. So yeah, so great application. Good. Oops. Let's see. There we go. And so let's go to application or classroom assignment 3. And it says complete the drawing of the car in the Bezier game and the letter activity. And these I'm not going to go through. You can go through. This is very simple. You kind of play with it. You can do the car or something, just so I know that you went through that and take an image. Let's see. And they're both like games, but they work, try to teach you how, and a lot of you may have already used these Bezier curves. So, and what they do is they just kind of give you a little introduction, and they say, okay, well, you can just go from there to there if you just go into straight lines, and so on. Now, skip the tutorial, and so if you want to do the car, they make it, of course, a little bit trickier, but they because these straight pieces, and then I'm off a little bit, but basically what they want you to do here is be able to see that to get the curve, uh, whoops, I'm going to make a curve from this point to this point, and then I'm going to use my control handle here to bend that thing around. Now I should be able to keep this horizontal and get that to work. So that works. And if you bend it in here, it bends it close to this point. If you move this out further, it bends it more away, over here. So if you stretch this out more, it bends it out closer to the other, takes it away from that. So you want to try to get it right to that level. And then again, I'm just kind of working with this mouse, and then, whoops. All right, so there we go. And again, you kind of have to do the same thing here. Oops. Bend that thing too much, bend it too much, and so on. And you kind of keep going around. If you want to bend this one, you could take this out. This program's a little bit hard to work with, but and so on. So that's it. That's pretty much the idea for that. And I'm just going to get out of this. Oh, there we go. So that's pretty much it for that. How many points in linear interpolation move when a cubic Bezier curve is formed? And again, what you need to do is just watch this, and it's short, it's interesting, and then you get to see how they're formed. It's really neat. Again, number 15, three current uses. Basically, you're just going to go through this and look at these. Each one's a use. This first one is a video. It's a long video, so there's only one part on Bezier curves. You may want to hold off on that, but uh, this one is about bridges, and let's see, I think this one is about a chair. Let's see, here's an application. We'll look at one of them, but you can see some applications. And if you kind of go down and look at these, the one in particular I was looking at was down here. So you say render stitch Bezier curves together to build a chair frame. So to do the curves, you kind of have to piece it together. This thing, you can't just draw one curve to get all of this, right? You're putting in multiple curves, and you're putting points, control points on them, control handles, and you're moving this thing to shape it. So it's a lot of work, to do something like that. But you can get pretty much any kind of design that you want. All right, so they're a great way to work with designs, and they generate the mathematics in the background for you automatically, so you don't have to deal with the math. I mean, you can still deal with math in lots of other ways, but this is one of those things that you can avoid it if you want. But there is a lot of math going on, and why are Bezier curves so popular? We're just gonna put this up here real quick. All right, so they say whoops, okay, here we go. Bezier curve, easy to use, can describe many shapes, famously used for representing characters and fonts and shapes in vehicles. They're also used in vector art packages for curve drawing, animation tools. They're popular because their mathematical descriptions are compact, intuitive, and elegant. They're easy to compute, easy to use in higher dimensions, 3D and up. and can be stitched together to represent any shape, and again, almost any shape you can imagine, but pretty darn close. So yeah, they're just a great thing to have and use. And the last thing, classroom assignment 4, create a design with Bezier curves. So real life application, something you should be thinking about for your project. And the myotes, again, it's being fussy. Sometimes it works, sometimes it's not. So you could try that. That's a very simple program that uses them. You can try Illustrator. There's some programs online that use Bezier curves, freebies, or again. So see what you can come up with on this, and if you have any questions or so, definitely call me. And remember, then the last thing, which is pretty much ends us for our activities throughout the course, and we just have next week. We'll be meeting for those final uh, summaries. All right, so stay healthy and see you next week.